So if you want to cripple a multi-billion-dollar military satellite that's hurtling through low Earth orbit at like 17,000 miles an hour, you don't actually need a top-secret space laser.
No, you really don't.
Right. You don't need an interceptor missile either. You honestly just need a pair of heavy-duty wire cutters and a map of a commercial power grid in Colorado.
Exactly. I mean, we spend so much time picturing military space operations as this pristine, futuristic battlefield, happening in the cold vacuum of the void.
Yeah, completely disconnected from the mud and the dirt of terrestrial warfare.
But the reality, the actual strategic reality, is that the entire architecture, keeping those incredible assets in orbit, is tethered directly to the ground beneath our feet.
It really is. And I think that's such a huge misconception for most people.
It is. The strategic vulnerabilities aren't always where the movies tell us to look. And that realization forces a massive shift in how you have to analyze modern warfare. If you are planning a joint operation across multiple continents, or you're tasked with understanding unified action across the competition continuum, you can no longer treat space as this benign sanctuary, or even just a mere supporting theater.
Right. It's the main event now.
It's a highly contested primary domain of conflict.
Yeah.
Our entire terrestrial military apparatus, I mean, from precision-guided munitions down to basic infantry communications, it assumes continuous, unfettered access to space capabilities.
And if you lose that access, you're back to, like, World War II technology in an instant.
Pretty much, yeah.
Which brings us to our mission for today's deep dive. We are stripping away the science fiction to examine the actual physical architecture and doctrine of military space operations.
Because you have to know how it physically works to understand the strategy.
Exactly. And our foundational map for this is Chapter 5 of the United States Army Space Reference Text. Specifically, we're focusing on space operations and the space system segments.
Great source material.
It really is. And we're looking at this through the lens of master's level military strategy. So that means we aren't just going to, list what these systems are. We are going to tear them apart to understand the physics, the engineering constraints, and the strategic calculus that dictate how they are used.
Right, because the doctrine we are pulling from outlines 10 specific space mission areas managed by the Department of Defense. But marching through all 10 would completely dilute the critical insights.
Yeah, we'd be here for days.
We would. So we are going to focus the lens intensely on the foundational elements, because everything in space strategy hinges on one non-negotiable prerequisite, and that is space domain awareness.
Space domain awareness, okay.
If you lack it, you're operating completely blind in an environment that is constantly trying to kill your equipment.
Wow, okay, but I want to pause on the terminology here, because the evolution is something we really need to parse out immediately. For decades, right, the gold standard phrase was space situational awareness.
Yes, exactly.
But now the doctrine strictly demands space domain awareness. To a casual observer, I mean, those sound like synonyms.
They do, yeah.
But at a strategic level, replacing the word situational with domain represents a massive leap in the required intelligence.
It's a huge leap. Think about the domain of submarine warfare.
Okay.
Space situational awareness is basically the equivalent of detecting a sonar ping. There is a physical mass displacing water at a specific depth and coordinate.
Right, you just know something is there.
Exactly. You can track its trajectory so your own ships don't accidentally collide with it. And that's essentially what we did in space for years, just cataloging objects to manage orbital traffic.
Like avoiding an expensive car crash in space.
Exactly. We just mapped the geometry of active satellites and, dead rocket bodies to avoid collisions.
Mm-hmm.
But space domain awareness is taking that initial sonar ping and layering on comprehensive intelligence, surveillance, and reconnaissance.
Oh, I see. So instead of just knowing a submarine is there, you're analyzing the acoustic signature of the propeller to identify the specific class of the submarine.
Yes, you're identifying the threat.
You're analyzing its patrol route to determine if it's running a routine deterrence mission or, setting up an ambush. You're listening to see if its torpedo tube doors are opening.
That level of predictive intelligence is the exact goal. Space domain awareness answers the who, the why, and the what next.
Which has to be incredibly difficult when you're looking at things hundreds of miles away.
It's staggeringly difficult. I mean, we are tracking tens of thousands of objects in orbit. Some are just dead husks of Soviet-era satellites. Others are pieces of shrapnel the size of a marble.
Wow, a marble.
Yeah, but when an active adversary satellite slightly elevates its orbit, Space domain awareness requires us to know, is it just doing routine station keeping to counteract atmospheric drag?
Because even in space, there's a little bit of drag, right?
Right, in low Earth orbit there is. Or, alternatively, are they maneuvering to intercept our communications architecture?
That's a terrifying distinction to have to make.
And you have to make it fast.
So, achieving that kind of granular intelligence across the vastness of orbit, that requires an absolute behemoth of an infrastructure.
Yeah, it really does.
The doctrine points to the space surveillance network as the engine driving this awareness. And this isn't, just a single telescope sitting on a mountain.
No.
It's a globally distributed web of optical sensors and radars. And the text categorizes these sensors into 3 distinct types, starting with dedicated sensors.
Right, so dedicated sensors belong entirely to the operational command, and their sole 24-hour-a-day mission is space surveillance.
Okay, so that's all they do?
That's all they do. They are geographically and technically optimized for absolutely nothing else. And the text specifically highlights the Maui Space Surveillance System in Hawaii.
Which honestly makes perfect sense from an optical physics standpoint. I mean, by placing a massive telescope at 10,000 feet above sea level, you bypass the densest layers of the troposphere.
Exactly, you get above the weather.
Right, you strip away the atmospheric turbulence that distorts the incoming light. And you're also isolated in the middle of the Pacific, which severs the sensor from the ambient light pollution generated by massive urban centers.
It's the perfect, pristine environment for looking up.
But optical telescopes can only do so much, right? Like, they struggle in bad weather, and they rely on reflected sunlight to see the objects.
Yeah, if a satellite is in the Earth's shadow, an optical telescope is practically useless.
Which is why the second category, collateral sensors, relies so heavily on radar.
Yes. And collateral sensors are fascinating because their primary mission has absolutely nothing to do with space surveillance.
Wait, really?
Yeah. The prime example the text uses is the Ballistic Missile Defense Radar installation in Clear, Alaska. The primary zero-fail mission of that facility is to scan the horizon over the North Pole, just waiting to detect intercontinental ballistic missiles targeting the North American continent.
Okay, wait, I have to challenge the mechanics of that.
Go for it.
If you have a radar installation whose sole purpose is watching for a literal civilization-ending nuclear strike, how does it simultaneously have the processing power, or even the bandwidth, to track a random piece of space junk floating by?
It's a fair question.
Doesn't the secondary mission inherently compromise the primary mission?
It absolutely would if we were talking about legacy mechanical dish radars, the ones that have to physically turn and point at a target.
Like the big spinning satellite dishes in old movies.
Exactly. But facilities like the one in Clear, Alaska, they utilize solid-state phased array radars.
Okay, phased array. What does that mean in practice?
It means they don't move. They steer their radar beams electronically by manipulating the phase of the radio waves emitted from thousands of individual antenna elements on the flat face of the building.
Oh, wow. So there's no moving part.
No moving parts, which means they can shift their focus from one target to another in milliseconds.
That's incredibly fast.
So the system can dedicate the vast majority of its computing power and energy to scanning for a missile launch, while simultaneously using fractions of a second of downtime to bounce radio waves off a passing satellite.
And then it just feeds that tracking data into the space surveillance network as a collateral benefit.
Exactly.
That's a brilliant exploitation of some costs. I mean, you've already built this massive infrastructure. You might as well pull secondary data from it.
You'd be crazy not to.
Which leaves the third category, contributing sensors. And these are operated by civil agencies, academic institutions, or allied nations.
Right. They aren't in the military chain of command directly.
But they share their data through formal agreements. Now, when you look at all 3 of these categories combined, the dedicated, the collateral, the contributing, you'd think we have a seamless blanket of coverage over the entire planet.
You would think so, yeah.
But the physical distribution of these sensors reveals a massive strategic vulnerability.
It's a glaring weak point. The geographic layout of the space surveillance network is heavily biased toward the Northern Hemisphere.
Because of the Cold War.
Exactly. Historically, that's where the major landmasses are, that's where the Cold War infrastructure was built to watch the Soviet Union, and that's where the primary technology bases reside.
So what does that mean for the Southern Hemisphere?
It creates profound blind spots. particularly over the vast expanses of the South Pacific and the Southern Atlantic.
But orbits operate on Keplerian physics, right?
Yeah.
They're continuous ellipses that wrap around the entire globe. A satellite doesn't just stay in the north.
No, it can't. It spends half its time dipping through the southern hemisphere.
And adversaries know this.
They're intimately aware of our terrestrial sensor architecture. I mean, you can't exactly hide a building-sized phased array radar in Alaska.
Right, they can just look at Google Earth.
So an adversary knows the precise minute their satellite slips out of the detection cone of our northern hemisphere sensors and enters that southern blind spot.
Wow, so it's like driving into a tunnel where the GPS cuts out.
Yes, and if they intend to conduct a hostile maneuver, perhaps altering their inclination, changing their altitude, or, deploying a stealthy subsatellite, they will execute that burn while out of sight.
So it becomes this incredibly tense game of orbital object permanence.
That's a perfect way to phrase it.
We watch an adversary satellite dip below the equator on the specific trajectory. We calculate exactly when and where it should reappear over a radar installation in Europe or North America.
Right.
And if it pops back up on our screens moving slightly faster or offset by a few degrees, we know they altered their velocity vector while we couldn't see them.
And that triggers a massive scramble. We then have to reverse engineer their new orbit and quickly assess what new threat they pose.
The burden of space domain awareness is just relentless.
It never stops.
But gathering the intelligence is really only the setup, isn't it? The strategic payoff is how a commander utilizes that intelligence to execute offensive and defensive space operations.
Exactly. Knowing the threat is step one. Doing something about it is step two.
And the doctrine gives us 5 distinct verbs for offensive action: deceive, disrupt, degrade, deny, or destroy adversary space systems.
But the critical strategic divergence here lies in how those effects are achieved.
Right. Because in terrestrial warfare, if an enemy tank is advancing on your position, you hit it with an anti-tank missile. The destruction is permanent, non-reversible, and highly localized. The tank is gone, and you move on.
But applying that kinetic logic to the space domain triggers catastrophic second-order effects.
Oh, totally.
The doctrine heavily prioritizes reversible attacks over non-reversible destruction.
Why is reversible so important?
The environment demands it. A reversible attack is an electronic or cyber effect that temporarily neutralizes the threat without altering the physical structure of the target.
Okay, give me an example.
Sure. Suppose an adversary reconnaissance satellite is passing over a sensitive military deployment on the ground. Instead of blowing the satellite out of the sky, you employ localized electronic warfare.
Like jamming it.
Exactly.
Yeah.
You aim a ground-based jammer at the satellite and flood its receiver with white noise, completely overpowering its command signals. Or you use a ground-based directed energy weapon, like a low-power laser, to illuminate the satellite's optical sensor.
Oh, I see. You're essentially shining a high-powered flashlight directly into a camera lens.
Yes. You saturate the focal plane array, dazzling the sensor, so it only registers a blinding white glare.
And the key is that it's temporary.
Precisely. The moment the satellite flies beyond the horizon, out of the line of sight of your laser or jammer, the interference stops. The satellite reboots, the optical sensors clear, and the system returns to its normal state.
The effect was entirely reversible, but you successfully denied the adversary the intelligence they were seeking during that critical pass.
You won the engagement without breaking the hardware.
And the motivation for relying on reversible effects becomes terrifyingly obvious when you look at the alternative. Because non-reversible kinetic destruction in space doesn't just eliminate the target, it pollutes the entire operating environment for everyone.
It's the ultimate scorched earth tactic, but in orbit.
And the text explicitly cites the 2007 Chinese anti-satellite test as the ultimate cautionary tale for this.
That event fundamentally altered the strategic calculus of every spacefaring nation.
What exactly happened?
China launched a direct ascent kinetic kill vehicle from the surface of the Earth, targeting one of their own defunct weather satellites at an altitude of roughly 500 miles.
So they shot a missile at their own satellite.
Yes. But the interceptor didn't use an explosive warhead. It relied purely on kinetic energy. It struck the weather satellite at closing velocities exceeding 15,000 miles an hour.
Oh my God, the physics of a hypervelocity impact like that are difficult to even comprehend.
It's mind-boggling.
Because it doesn't just break the satellite into a few large chunks like dropping a plate. It obliterates the molecular structure of the materials. It instantly converts a solid 2-ton object into a massive expanding cloud of shrapnel.
Yes. And furthermore, In the near vacuum of low Earth orbit, there is virtually no atmospheric friction to slow those fragments down.
So they just keep going.
They maintain the orbital velocity of the original satellite. That single test generated thousands of pieces of debris large enough to be tracked by our radar systems, and an estimated millions of fragments too small to track.
Millions.
Millions. And they are traveling fast enough to punch a hole straight through the hull of a manned spacecraft or shatter the optical lens of a multi-billion-dollar intelligence satellite.
Which plays directly into the concept of Kessler syndrome, because the debris cloud doesn't just stay clumped together in one spot.
No, it spreads.
Over months and years, variations in the gravitational field and minute drag forces cause those fragments to spread out, eventually encapsulating the entire planet in a lethal shell of high-speed shrapnel.
It essentially turns that specific orbital altitude into an indiscriminate minefield.
That threatens our assets, allied assets, and ironically, China's own future space architecture.
It guarantees mutual orbital destruction. This is why non-reversible kinetic attacks are viewed not just as acts of war, but as acts of environmental vandalism that degrade the utility of the domain for generations.
It's completely self-defeating.
It is. Consequently, if we are prioritizing electronic, cyber, and directed energy warfare for our offensive operations, we must assume our adversaries are targeting us with the exact same reversible yet highly disruptive methods.
Which forces us to engineer incredibly robust defensive space operations.
We have to.
And the doctrine splits defense into active and passive measures. Passive defense seems to revolve entirely around mitigating the physical realities of the environment and the anticipated electronic threats before the launch sequence ever begins.
Right. You are baking resilience directly into the hardware. You build the armor into the architecture.
Like radiation hardening.
Exactly. A primary component of passive defense is radiation hardening. Satellites are bombarded constantly by the natural radiation of the Van Allen belts and solar flares.
Just naturally.
Just naturally. But they must also survive the localized electromagnetic pulse of a potential high-altitude nuclear detonation.
Wow. And standard commercial microchips would just fry instantly in those conditions, wouldn't they?
In a heartbeat.
Yeah.
Military space systems require specialized, heavily shielded circuitry.
What about the electronic warfare piece?
Passive defense also dictates the use of highly complex, frequency-hopping cryptography for the command links. You have to prevent adversaries from spoofing the satellite and taking control of its systems.
Oh, so they can't just hack in and steal it.
Right.
The doctrine also mentions architectural proliferation as a passive defense.
Yes, that's a huge shift.
Instead of putting all our capabilities into a single massive satellite the size of a school bus, which, let's be honest, represents a terrifying single point of failure, we deploy constellations of dozens or hundreds of smaller interoperable satellites.
It's the don't put all your eggs in one basket strategy.
Exactly. If an adversary manages to jam or blind 3 or 4 of them, the network simply reroutes the data through the surviving nodes. It dilutes the value of any single target.
It makes an attack mathematically exhausting for the enemy.
But passive defense only absorbs the punch, right? What happens when you need to actively dodge it?
Well, active defense in orbit is a brutal exercise in resource management.
Why is that?
Because if our space surveillance network calculates that a piece of debris, say from that 2007 Chinese test, is on a direct collision course with one of our critical assets, the ground controllers must initiate a maneuver.
They have to move it out of the way.
Yes. They send a command to the satellite to ignite its thrusters and physically alter its orbit to evade the impact.
But maneuvering in space carries a permanent, irreversible penalty. Satellites don't exactly have gas stations up in orbit.
No, they don't. They launch with a finite amount of hydrazine propellant, which is known as their delta V budget.
Delta V, meaning change in velocity.
Exactly. And every single time you execute an active defensive maneuver to dodge debris or an adversary's co-orbital weapon, you burn a fraction of that irreplaceable fuel.
And when the fuel is gone.
And the fuel is gone, the satellite is dead.
Just like that.
Just like that. It can no longer maintain its precise orientation, its solar panels drift away from the sun, the batteries die, and its orbit slowly decays until it burns up in the atmosphere.
So adversaries know this.
Oh, they definitely know this.
Which means they can wage a war of attrition without ever firing a shot. They simply maneuver their assets aggressively, forcing our satellites to constantly burn precious fuel, dodging phantom threats, until their operational lifespans are drastically reduced.
It's an invisible game of chicken that costs hundreds of millions of dollars.
That dynamic really forces us to expand our definition of what a space system actually is, because it's so easy to focus obsessively on the satellite itself, maneuvering out there in the dark.
It's the shiny object.
Right. But the doctrine clearly mandates that a space system is fundamentally composed of three interdependent segments: the space segment, the ground segment, and the link segment.
And isolating your strategic analysis to just the space segment, meaning the physical hardware in orbit, is a fatal flaw.
Yes.
A satellite is entirely reliant on terrestrial infrastructure.
I think the best way to visualize this architecture is to look at modern remote autonomous systems, like a high-altitude military drone.
That's a great analogy.
You have the airframe itself loitering at 60,000 feet. That's your space segment.
Okay.
Then you have the pilots and intelligence analysts sitting in a secure facility in Nevada, surrounded by servers and massive communication dishes. That's the ground segment.
Right.
And then the invisible tether connecting the encrypted radio frequencies, transmitting the flight commands up and streaming the high-definition video down. That's the link segment.
And an adversary looking to neutralize that drone doesn't necessarily target the heavily defended airframe. They look for the path of least resistance across all three segments.
Exactly. Why invest billions in developing an anti-satellite missile to attack the space segment when you can just hire a team of cyber operatives to hack the commercial power grid supplying electricity to the control facility in Nevada?
It's so much cheaper and easier.
You cripple the ground segment. The servers go dark, the command console shut down. The satellite is physically untouched up in space, yet it is rendered completely inert.
Or, they target the link segment.
How does that work?
They deploy localized electronic jammers near the tactical units on the battlefield who are trying to receive the satellite signal. The satellite is broadcasting perfectly, the ground station is operating normally, but the receiving antenna on the ground is overwhelmed by static noise.
The information never reaches the warfighter.
Exactly. The loop is broken.
This interdependency completely rewrites the risk assessment of space operations. We have to secure the terrestrial power lines and the invisible electromagnetic spectrum just as fiercely as we secure the physical orbit.
We do. But let's isolate the space segment for a moment, though, because the doctrine breaks the actual spacecraft down into two distinct anatomical parts: the platform and the payload.
The platform and the payload.
Right. The aerospace industry often refers to the platform as the bus. It is the host vehicle. Its singular purpose is to keep the satellite alive and positioned correctly in the unimaginably hostile environment of space.
It provides the basic metabolic functions.
Exactly. It houses the structural frame, the thrusters for maneuvering, and the massive solar arrays that convert sunlight into electrical power.
But the most critical and often overlooked function of the platform is thermal management, isn't it?
Yes. Thermal control in a vacuum requires profound engineering.
Because down here on Earth, if a computer server gets hot, we just blow air across it with a fan. Convection carries the heat away.
But in space, there is no air. Convection literally doesn't exist.
Which is wild to think about.
It is. Furthermore, the side of the satellite facing the sun is bombarded with intense solar radiation, heating up to hundreds of degrees, while the side in the shadow is exposed to the ambient cold of deep space, dropping to hundreds of degrees below zero.
So you have a vehicle that is simultaneously baking on one side and freezing on the other, with incredibly delicate electronics trapped inside.
The platform must actively and passively manage that extreme temperature differential.
How does it do that?
It uses multi-layer insulation, those gold foil blankets you often see in photographs of satellites, to reflect the solar radiation.
Oh, that's what those are.
Yeah. And internally, it uses heat pipes containing ammonia to absorb thermal energy from the internal computers and pump it to external radiators pointing into deep space, shedding the heat via infrared radiation.
That is so complex.
And if the platform's thermal control system fails, the electronics will literally cook themselves to death within hours.
So the platform does all the heavy lifting, so the payload can do the actual mission.
Yes. The payload is the cargo. It's the entire reason the satellite was launched in the first place.
Right. If the system is designed for missile warning, the payload is a highly sensitive infrared telescope looking for the heat bloom of a rocket exhaust.
Exactly. And if it's a communications satellite, the payload is a complex array of transponders that ingest faint radio signals from the Earth, amplify them, and blast them back down to a different continent.
The platform is the truck, the payload is the freight.
That's a perfect analogy. And because the spacecraft is divided into these two functional halves, the ground segment has to exercise very different forms of control over them.
Which the doctrine defines as three distinct mechanisms of command: platform control, payload control, and network control.
Right. This represents the strict division of labor within the operation centers. Platform control handles the health and safety of the bus.
These are the orbital mechanics experts and systems engineers.
Exactly. They monitor the degradation of the solar panels, they manage the thermal fluid pressures, and they calculate the precise duration of a thruster burn required to maintain the satellite's altitude against the microscopic drag of the upper atmosphere.
They are essentially the flight crew keeping the plane in the air.
Right. But they aren't the ones taking the photos or routing the communications.
That falls to payload control.
Yes. Payload control is executed by the mission specialists. They operate the cargo, they send the commands that angle the optical sensor toward a specific coordinate, or they adjust the frequency bands on the communication transponders to support a specific military operation on the ground.
And wrapping around all of this is network control, which honestly feels like the unsung hero of the entire architecture.
It absolutely is. Network control is the monumental task of managing the link segment.
Because we have finite numbers of massive satellite dishes on the Earth, but we have hundreds of satellites flying overhead.
Exactly. You have a massive bottleneck. So network control dynamically schedules which ground antenna talks to which satellite at what specific minute on what specific frequency.
Just to make sure that the commands from the operators actually reach the hardware.
And to ensure that the massive streams of data from the payloads are routed securely through terrestrial fiber optic cables to the commanders who actually need the intelligence.
It's like managing the busiest airport in the world, but the planes are traveling thousands of miles an hour.
And you can't see them.
Right. Which brings us to the final critical piece of the strategic puzzle. We've mapped out the domain awareness required to see the battlefield. We've covered the offensive and defensive doctrines and the intricate architecture of the segments.
But none of that matters if you can't actually put the hardware into orbit.
Exactly. The doctrine heavily emphasizes the strategic necessity of spacelift.
Because assured access to space is the absolute foundational pillar of space power.
If you lose the ability to launch payloads, your space architecture will just slowly degrade and die. It's a ticking clock. And the spacelift paradigm has undergone a completely revolutionary transformation in recent years. We are shifting away from an exclusive reliance on massive government-managed rocket programs to a really aggressive integration of the commercial launch industry.
And this shift fundamentally alters the economic and strategic calculus of the domain.
Yeah.
Because historically, launching a military satellite was this bespoke, multi-year endeavor.
Oh, it took forever.
The rocket was custom-built, it flew once, and the booster just dropped into the ocean and sank. It cost astronomical amounts of money, meaning the military could only afford to launch a few incredibly expensive satellites.
And because those legacy satellites were so expensive and so difficult to replace, they became massive strategic vulnerabilities.
Targets.
Huge targets. If an adversary managed to disable one, they created a permanent gaping hole in our communications or intelligence architecture. The loss was catastrophic. But the advent of commercial reusable rockets has shattered that paradigm. We aren't building custom galleons anymore. We are buying cargo space on a fleet of commercial freighters that run routine schedules.
The commercial industry has driven the cost per pound to orbit down by orders of magnitude.
It's incredible.
Rockets are launching weekly, sometimes multiple times a week. The first stage boosters are landing and flying again. And this commercial capability allows the military to actually embrace the proliferation strategy we discussed earlier.
Right. Instead of spending $2 billion in 10 years building one exquisite satellite, you spend the exact same amount building and launching a constellation of 100 smaller, cheaper satellites on commercial rockets.
And this concept of rapid reconstitution drastically reduces the incentive for an adversary to attack in the first place.
Oh, that makes sense, because if an adversary expends a massive amount of capital and risks international condemnation to blind or jam 3 of our satellites...
the strategic benefit is negligible.
Right, because we can simply load 3 replacement satellites onto a commercial rocket and have them operational in orbit within 48 hours.
The commercial spacelift industry has provided an unparalleled level of architectural resilience. It changes everything.
So the commercial rocket roars off the pad, pierces the atmosphere, and deploys the satellite into the vacuum. The solar panels unfurl, the systems boot up, the spacelift mission is complete.
But now begins the grueling, decade-long marathon of spacecraft operations.
And the doctrine dictates that the absolute lifeline of these operations is telemetry, tracking, and commanding.
Telemetry, tracking, and commanding constitute the critical data flows within the link segment. Without this specific flow of data, a satellite is completely uncontrollable.
Let's dissect the physics of how this actually works, starting with telemetry. Telemetry is the continuous stream of diagnostic data flowing downward from the space segment to the ground segment.
Right. The satellite is constantly interrogating its own internal systems.
It measures the voltage flowing from the solar arrays into the batteries. It measures the temperature of the reaction wheels used for orientation.
It encodes all of this diagnostic data into a complex digital signal, modulates it onto a high-frequency radio wave, often in the S-band or X-band of the electromagnetic spectrum, and beams it down to the Earth.
The ground operators rely on that telemetry to anticipate failures before they ever occur. It's like the ultimate check engine light, but from 20,000 miles away.
That's exactly what it is. If the telemetry stream indicates a minute drop in pressure in a hydrazine fuel line, the operators know a valve is leaking.
They can fix it before it's too late.
They can switch to a redundant system before the fuel is completely vented into space. Telemetry is the autonomic nervous system of the spacecraft reporting its status.
While telemetry tells you the health of the satellite, Kraken tells you its exact physical location. We talked earlier about the space surveillance network tracking objects, but this is a much more intimate, active process, isn't it?
Yes, very active. The operations center needs to know the satellite's position down to the meter.
How do they do that?
They transmit a highly synchronized radio signal from the ground antenna up to the satellite. The satellite immediately echoes that exact signal back down.
Like radar, but with a transponder.
Precisely. By measuring the microscopic time delay between transmission and reception, and factoring the Doppler shift of the radio wave caused by the satellite's immense velocity.
The computers on the ground can calculate the precise orbital trajectory.
Exactly. You must have this tracking data. Otherwise, you simply won't know exactly where to point your ground antennas for the next communication window.
And you desperately need that communication window to execute the final and most sensitive element, commanding. Telemetry and tracking flow down. Commanding flows up.
Commanding is the exertion of control. These are the heavily encrypted data packets sent from the ground segment that dictate the satellite's behavior.
What kind of behaviors?
Well, a command could be a line of software code patching a vulnerability in the payload's operating system. Or it could be a sequence of timed instructions telling the platform to ignite its thrusters for exactly 4.2 seconds to avoid an incoming piece of debris.
The encryption on the commanding link has to be virtually unbreakable then.
It has to be. If an adversary cracks the encryption and successfully spoofs the commanding link, they effectively steal the satellite.
Wow.
They can send a command instructing the satellite to fire its thrusters until its fuel is exhausted, or command it to permanently shut down its solar arrays, basically killing the battery.
But even if they can't break the encryption, if they can simply deploy a powerful enough jammer near our terrestrial ground antennas to overpower the signal with white noise, they sever the link segment anyway.
And we arrive precisely back at the strategic vulnerability we highlighted at the very beginning of this deep dive.
It's a full circle.
It is. The satellite could be structurally perfect, fully fueled, and operating optimally in a pristine orbit. But if the ground segment cannot transmit the commanding signal, or the satellite cannot downlink its telemetry, the system is dead.
A multi-billion-dollar asset is reduced to a piece of high-velocity space junk without a single physical shot being fired.
Exactly.
It is an incredibly fragile, interdependent web. We started this deep dive by establishing that space domain awareness is the foundational bedrock requiring massive phased array radars and optical telescopes to characterize threats in an unforgiving domain.
Right.
We explored how the terror of Kessler syndrome dictates our reliance on reversible electronic offensive operations rather than kinetic destruction. We analyzed the spacecraft architecture, stripping it down to the platform managing the thermal extremes of the vacuum, and the payload executing the mission.
And we proved that the entire enterprise relies on commercial spacelift for resilience and a highly vulnerable link segment for control.
It's so much more complicated than just rockets and lasers.
It is. And the synthesis of all these doctrines is that space operations do not exist in a vacuum, strategically speaking. I want you, the listener, to deeply internalize this reality.
It applies to everything.
It really does. Whether you are analyzing a brigade-level ground maneuver relying on precision navigation or a naval strike group coordinating over satellite communications, you are entirely tethered to this architecture.
Space is the invisible central nervous system.
The invisible central nervous system of modern unified action. If the space segment, the link segment, or the ground segment fractures, terrestrial operations degrade immediately.
Which requires a fundamental shift in perspective for all of us. We dedicate immense intellectual and financial capital to worrying about interceptor missiles and co-orbital weapons attacking our satellites in the deep black of orbit.
Because it's flashy.
Right, it looks good on a PowerPoint. But considering how heavily these platforms rely on the uninterrupted flow of the electromagnetic spectrum and how totally dependent they are on terrestrial command centers plugged into civilian power grids, I want to leave you with this provocation.
Let's hear it.
The ultimate Achilles heel of our futuristic space architecture isn't located hundreds of miles above our heads. It's buried in the fiber optic cables and the commercial power infrastructure right here, with both feet firmly planted on Earth.
It forces us to redefine where the battlefield actually begins.
It really does. Thank you for joining us on this deep dive into the military space domain and for stepping past the cinematic illusions to confront the strategic reality. We will catch you on the next deep dive.